Guitar Hero and political things. People arguing. Arguing over
do you
Guitar
play
Hero.
unboxing videos of like watches and stuff like that?
Typically not unboxing videos because I think that's a bit of a cheap way to get views. I mean, you're just watching someone. You're literally watching someone open something that you don't have the privilege of opening yourself. But during certain periods of time, I do follow like certain like watch-related channels, and they talk about the watches. And it's pretty cool. I like that.
Yeah. All right, and then so idea is that in general relativity, we expect, okay, I've got this mass. It's making a gravitational field. Far away from the mass, where gravity is weak, you ought to be able to ignore it, and so space-time ought to be flat out there. So that's one kind of principle. Far away from a mass, space-time ought to be flat, and the Minkowski metric, the dt squared minus dx squared minus dy squared minus dz squared, ought to work out there. The effects of gravity show up, and then when you get close to the mass, there's these other terms in the metric that become more and more important. So, in GR, we expect space-time far from a mass to be flat, so the metric goes to the SR metric at large distances. And if the mass is not spinning, we ought to have spherical symmetry. I'll say if the mass is spherically symmetric, just to be really specific, if the mass is spherically symmetric and not spinning, we must have spherical symmetry. Spherical symmetry, note, means there's no special direction in space. So why would spinning ruin that? If you had spinning, would there be a special direction in space? What's this?
What do you mean by special direction?
In other words, I don't know how else to put it, a direction which is distinguished from other directions. So if there's spherical symmetry, every direction is equivalent. So a special direction is one that's picked out as being different from other directions. So if something is spinning, there is a special direction. What is that special direction?
The direction of the spin.
Yeah, the rotation axis is a special direction in space. It's different from other directions. It's the direction towards which the rotating object is pointing. Earth is pointing nearly at the star Polaris. That makes Polaris appear to move very differently in our sky than other stars do because it's close to the North Celestial Pole. If Earth were not spinning, we would not have that asymmetry in how the stars appear, in that no stars would be moving across our sky if Earth were not spinning. So the rotation axis is a special direction in space if you have something that's spinning. So if there is no spinning and the mass is spherically symmetric, the metric must be spherically symmetric. If it's spinning, then there would have to be some artifact of that in the metric, something that picks out the direction that the object is spinning in, this axis of rotation. And I'm going to stop that because I need chalk. I'm looking and I don't see any chalk. And you know how I refuse
It's a non-symmetric spinning metric.
Ah. No, I think that should be all right. I don't think there's any other. I know. What is your webinar?
What?
Today?
What?
Is this today?
Yeah, it's at 4.
Oh, okay.
Yeah, that's what I meant.
Yeah, that should be doable, yeah.
Yeah.
Or
It's like-
example. If the mass is spherically symmetric and not spinning, then we must have spherical symmetry. And the metric must be spherically symmetric. In flat space-time in spherical coordinates, we have that ds squared is, I'm going to put in c here because it shows up in the Schwarzschild metric, and on a first exposure it's better to see the c where it belongs in there. C squared dt squared minus, and then we've said this before, minus dr squared minus r squared d theta squared minus r squared sine squared theta d phi squared. In other words, the increments of distance in the three directions show up in the space part of the metric. And then you've got the usual c dt quantity squared as the time part of the metric. When Einstein first wrote down what are called the Einstein equations that allow you to calculate the metric for a given distribution of mass and energy, he thought that it would be impossible to explicitly solve them, but he was wrong. Karl Schwarzschild, on a World War II battlefield in 1916, found the unique spherically symmetric solution to the Einstein equations.
World War
sent
II
to
battlefield?
Einstein. What's that?
World War II battlefield?
World War I battlefield, I meant to say.
I was like,
World War
yeah.
Yeah, World War I, yeah. was
Traveling in time already.
World War II, yeah, that's right. In his brain. Right.
It was 1916.
Yes, but, yeah, okay, I'm speaking nonsense here.
Oh, we are not being shot at anymore? Okay, time to do math.
Except he was German, not Russian.
Oh. Okay, time. Just make him sound angrier.
Right. All right. The only spherically symmetric static metric, as it is not time dependent, the only spherically symmetric static metric, static means time independent, that satisfies the Einstein equations is the Schwarzschild metric. Obtained on a World War I battlefield by Karl Schwarzschild in 1916. WW1 battlefield.
I just can't get over the battlefield part. That is just.
It is amazing, isn't it? Yeah, it is amazing. Well, then he proceeded not long after to die of typhus. So it's actually a very sad story.
Weren't the early 1900s grand?
They were just wonderful, yes. So
20th
much
century,
talent.
that was the place to be.
So much useless genius was wasted back then.
Illusion.
We're getting ready to do it again, it seems like these days. But anyway, obtained on a World War I battlefield by Karl. Oh, I shouldn't have started writing that there. make it. Schwarzschild
Damn it, Carl.
in 1916, just 2 months after Einstein published GR.
Einstein's like, it will never be done. And then I'm, oh shit, look at that.
Yeah. Yeah, I sent the solution to Einstein, and let's just say Einstein was impressed.
Oh, well, crap.
ds squared is c dt times the square root of 1 minus 2gm over c squared r, quantity squared, minus dr over the square root of 1 minus 2gm over c squared r, quantity squared, minus, probably should have written the other metric, the flat space-time metric with parentheses 2, just to be consistent with how I'm writing it here, minus r d theta squared minus r sine theta d theta squared. So yeah, I'll just do that here. You don't have to rewrite yours, but it does make it more obvious how they're related to one another. So notice that the angular pieces don't change. The last two terms look the same. It's the time piece and the radial piece which are different because of the presence of gravity when we have spherical symmetry. Right? dr is replaced by dr over this square root, and dt is replaced by dt times that square root right there. So m is the mass of the body providing the gravity. It's spherically symmetric because notice that it looks just like the flat space-time metric, and in particular the angular pieces are the same. The angular pieces are the ones that talk about direction away from the center. There's no preferred direction away from the center. I mean, there's a z-axis, but the z-axis could have been in any direction. So there's no specified direction. It needs to be the polar axis. It needs to be the z-axis. It applies only in the empty space outside the mass. It doesn't apply inside the mass. Only applies outside the mass. So, as you get far away from the mass, r goes towards infinity. What happens to the square root term as r goes to infinity? What happens to 2gm over c squared r when r gets very big? What does it approach?
Goes to 0.
Goes to 0. So the square root term goes to 1. So, in fact, at large r, this does become the flat space-time metric like we wanted. As r goes to infinity, ds squared goes to the SR metric as expected. far away it looks like flat space-time. However, r is not simply distance from the center. It is in the flat space-time metric. In the flat space-time metric, r is just how far you are away from the origin. But here, r is not distance from the origin. R is not simply distance from the origin. And in particular, here's a trick of the sort that we'll use a lot. If we set dt equals d theta equals d phi equals 0, then we're considering two events which only differ in their radial coordinate. dr is the only thing that isn't 0. We're just looking at two events along a line from the center. So in that case, if we plug in to the metric, we see that ds squared for events with that relationship, because dt, d theta, and d phi are all 0, ds squared is minus dr over the square root squared. Okay? And we make the same interpretation of the interval that we do in flat space-time. In other words, if I have ds squared is less than 0, just as in flat space-time, when ds squared is less than 0, then the square root of minus ds squared is the what between the events? What did we say that minus square root of minus ds squared represents when ds squared is less than 0? Is that proper time or proper distance in that case?
Proper distance.
It's proper distance. It's proper distance. It's got to be because we set dt equals 0 here, so it can't be proper time. That's the proper distance between the events. And the physical interpretation of proper distance is its actual meter stick distance. It's an actual distance you would measure with a meter stick or a measuring tape. With a measuring rod to be compared. So the distance between those events is dl equals dr divided by the square root of 1 minus 2 gm over c squared r. In other words, it's not equal to dr. And if you think about it, the square root there is less than 1, right? Because it's the square root of 1 minus something. So the square root is less than 1. So if we divide by the square root, we're dividing by a number less than 1. So dl is in fact bigger than dr is. So what does this mean? This is what it means. So the Schwarzschild metric is 3 dimensions of space, but if you compact it down into 2 dimensions, or if you just consider the equatorial plane, then in fact it's equivalent to this funnel-shaped drawing right here. In other words, it's equivalent to taking this curved surface and measuring distances along that curved surface. So let me allow the viewer at home to see this figure.
It is too precious for me.
So here you go, Alec. There you go. It's kind of nice to actually be really talking to somebody here for sure.
Yeah, he's not worth it. He's probably not gonna watch it.
Yeah, he's probably, no, he really should.
He will.
I think he will. I think he will.
Especially with all the time given some break.
Yeah.
If he doesn't, that's just irresponsible. Hear that, Alec? I'm calling you out.
Alec, if you watch this, at some point you have to come up to me and say, I like pink elephants. Right? Got it? I like pink elephants. If you say that, I'll know that you actually watched this. If you never say, I like pink elephants to me, I'll know that you didn't actually watch this. Okay? Got it?
Lame there. You're gonna have some student in like 15 years come up to you and just be like, I like pink elephants.
It's not.
And you're just be like, what?
What?
What are you talking about?
I'll be like, Right. So, for people watching this will have no idea what as well. Well, Alec would though, because we talked about it in Anyway, so these in this funnel here, which actually has the right shape to be described by the Schwarzschild metric, but only in the equatorial plane. In other words, you set theta equal to 90 degrees, then the metric that describes is in fact the metric spatially on a sheet having this shape. You can actually draw the 2-dimensional shape such that distances in space along that shape are correctly described by the Schwarzschild metric, which is why black holes are illustrated with these funnels all the time. That's actually a physically realistic thing to do in the equatorial plane. So the circles are circles of constant radial coordinate. As we're about to see, the radial coordinate is defined to be the value of r that gives the right circumference for the circle, or in 3 dimensions, the right area for the sphere. But notice, on this curved rubber sheet, there's no distance to the center because, in fact, if it's really just Schwarzschild metric everywhere, this funnel goes down forever. So distance along the sheet to the center is actually infinite. R isn't distance from the center. R isn't distance along the sheet. R is the difference in the, R is, as we'll show in a second, R, a little more in a second, R is the value that makes the circumferences of these circles be 2 pi r. Or in 3 dimensions, it's the value that makes the area of the sphere be 4 pi r squared. So in other words, r is really is the square root of a over 4 pi, where a is the area of the sphere. Or on this sheet, it's the circumference divided by 2 pi is what r actually is. But because of the curvature of the sheet, notice that the distance between 2 circles having given values of r is bigger than what you would get for a flat sheet between circles having those same radii. And that's what that's represented. Distance along the sheet is bigger than what you would get for the distance between circles having those two circumferences and corresponding radial values. So you can understand this as an artifact of the curvature of the space. You're moving along a curved surface, which means you have to go further to get between circles of given circumferences than you would on a flat sheet. Does that make sense? Any questions? So let's continue with that. Consider a sphere of constant r, so events on that sphere at any given time as specified by t. We'll see that the interpretation of t is interesting too. T we'll see is what we call faraway time. Time is measured far away from the mass. So events on that sphere at any time as specified by t have dt equals dr equals 0, but d theta and d phi, but d phi does not equal 0, d theta does not equal 0, and d phi does not equal 0. In other words, if I've got two events on the surface of that sphere, there's no r difference between them, there's no time difference between them, but they have different values of theta and phi. Any two points on the surface of the sphere at instants of time, any two events on the surface of that sphere, surface of constant r at an instant of time, have non-zero d theta and d phi between them, but 0 dr and 0 dt. Okay? So, if we find the area of the sphere, this is A equals, well, we're going to have to integrate over the surface, so to integrate over theta and phi, integral from 0 to 2, integral from theta equals 0 to pi, phi equals 0 to 2 pi, and we're adding up the areas of all the little rectangles on the sphere, but the pieces in the theta and phi directions for constant r have lengths r sine theta d phi and r d theta, just like in our beloved spherical coordinates that we always talk about. So the area of a little rectangle is just like in standard spherical coordinates, r squared sine theta d phi. Because the metric is telling us distances, and it's telling us that the distances are in fact r sine theta d phi and r d theta, so the area is in fact r squared sine theta d phi for a little rectangle on a surface of constant r at constant time. Well, we know what this adds up to. What does this add up to?
It's a thing that I know, but I forget every now.
Is not sine theta d theta d phi d omega,
Oh,
right? And what do you get when you add up d omega over the entire surface of this, over all angles? You get the total number of steradians in a sphere, which is 4 pi. That angular integral is 4 pi. So this gives 4 pi r squared. Of course it does. The area of a sphere is what you get by adding up the area of all the little rectangles, and that's 4 pi r squared. So by definition, our metric is implicitly defining what r means. By definition, the area of a sphere is 4 pi r squared. The area of a sphere of constant r, in other words, a sphere that has the origin at the center, the area of a sphere. I mean, not all spheres have constant r. In other words, if this is the origin, here's a sphere, and that has variable r values, right? It's only ones that are centered on the origin that have constant r. The area of a sphere of constant r is 4 pi r squared. In other words, r is defined to be the square root of a divided by 4 pi. Ah, yes. So, if you actually watch this, you have to say blue elephants, however, are ugly. So little ants crawling around on the sphere could measure its area and use that to find r without having to try to find the distance from the center. And similarly, here on Earth, right? Nobody ever drilled a tunnel to the center of the Earth and dropped a measuring tape down it and then measured the radius of the Earth that way. What we did was measure the Earth's curvature and use that to infer the radius of the Earth. So in the equatorial plane, theta equals pi over 2. We have ds squared is, and because it gets tiresome, sometimes I'll just write square root with nothing in it, and it's understood to be the stuff inside the square root. metric looks like that, because if theta is pi over 2, sine theta is 1, so the r sine theta d phi just becomes r d phi. In other words, we've just got essentially the equivalent of polar coordinates in the equatorial plane. But again, we've got this funny dr over the square root being the distance. And that's what's described by this stretched rubber sheet analogy. Shape described by the spatial part is the classic quote-unquote funnel that is used to represent a curved space around a gravitating mass. All those popular level descriptions where they show the funnel to represent curved space-time, all that business, what that is representing is precisely the Schwarzschild metric in the equatorial plane. But notice the spherical symmetry says it doesn't literally have to be the one where theta is pi over 2 relative to some z-axis, because any direction is equivalent. So really, any plane that passes through the equator is described by that same metric if you put spherical, if you put polar coordinates in that plane. It doesn't have to be literally the equatorial plane around some particular arbitrary z-axis. Okay, any questions? Yes?
So, like if you looked at a different plane that's not the equator, would it also have that funnel characteristic?
It would, but it wouldn't have quite the same shape. Like in other words, if like here's the mass and you pick another plane, yeah, it wouldn't be exactly the same shape in that case, but it would have that funnely characteristic, yes.
Do they like connect? Would they all connect?
Yeah, they would. Yeah, we're drawing analogies here, okay? So, in the analogy, we can't visualize how they're connected because we're talking about curved three-dimensional space when you do that. But here's what it's analogous to, is this slice out of the three-dimensional curved space is equivalent to if space were two-dimensional, so that this was the space around a two-dimensional disk of mass, then taking the equatorial slice is equivalent to jumping, notice the equatorial slice is jumping down into 2 dimensions out of 3. Here we would want to jump down into 1 dimension instead of 2. In other words, we would take any slice, any one-dimensional straight line slice that passes through the center, so that you had just this line, okay? So then your question of, well, what if it's not including the center? Would you still have that kind of funnel characteristic? Yes, because what would be equivalent to be doing that in a two-dimensional space is a line which doesn't pass through the center. That would still bend, right? But it wouldn't have exactly the same shape. So we can see how they connect, right? Far away, it's flat. As you get closer and closer, it bends more and more. Slice, 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 slice. We can see how they connect. There's something I can't visualize and you can't visualize that's analogous for how slices not going through the center connect to make the curved three-dimensional space-time. How all those curved two-dimensional slices connect to make the curved three-dimensional space-time, which is analogous to all these curved one-dimensional slices connecting smoothly into a curved two-dimensional surface.
Okay.
That
Yeah,
would be,
makes sense.
yeah. I can't picture it, but I know it must exist for some creatures who are able to think in higher dimensions. They'd be able to say, oh yeah, it just looks like this, right? So that's kind of the idea there. Why don't I just stop here? Yeah. I guess I should have been pointing at this figure right here when I was talking about Derek's question, wherein I was saying, okay, the analogy of slicing through the equator is slicing in a straight line that goes through the center, whereas if I slice through a plane that goes above the center of the sphere, for example, that's equivalent to a one-dimensional slice that doesn't go through the center of our two-dimensional curved surface.